which is a very, very reputed premier institute of the country. And he served there as a scientist. After that, he is, I shouldn't use the word retirement from the NII. After he left NII, he joined as Pfizer Pune as a visiting faculty or adjunct faculty. Along with this role as a teacher, as a medical practitioner, and as a scientist, he is basically also attached with so many government association for the society related activities, making policies and science, along with his activities and in so many journals, reputed journals in the editorial form. So today, when 2020, 2021, people are basically shivering, shuttered with corona pandemic, I think he is the best person. And the last day, the he can enrich us, enlighten us about this corona pandemic from his title of the thing, COVID-19. So I know Professor Roth do not need any introduction. So he himself a class and a genius. It is just a single word he deserves. But those who do not know, just this is for them. But kindly forgive me if I made any mistake. I know it's a very, very little thing about you. And we are really proud when people are saying Professor Roth is coming. I am extremely honored as a coordinator of this FTP program. And actually, there is nothing to say about it. I think there was so more than this. So with this little introduction, I humbly request Dr. Roth, Professor Roth, to kindly take over the session.
Thank you very much, Professor Banerjee. That was a very flattering introduction, and while it was quite correct on all facts, it is not at all correct with respect to all the.
No flattering, sir. It is basically what is actually as being a scientist. You are being a scientist, and I try to work. So, what is the fact? I give the factual statement.
So, as Professor, good morning to everybody. And as Professor Banerjee pointed out, this is a 6-day webinar series under the title of Biology for Mankind. It's at the Maulana Abul Kalam Azad University of Technology of West Bengal. So, I thought that when Professor Banerjee invited me to speak, that there were a couple of limitations and a couple of opportunities here. The limitations are, I don't know, I don't use audiovisual aids particularly well. And in an online session of this sort, that creates difficulties because you people are left with staring at my face on the screen, which is, I can imagine, very boring. On the other hand, especially when the group is small and there's about 20 odd of us, it does provide opportunity for us to have actual conversations. So I had said to Professor Banerjee that what I would much rather do is have a more of a discussion than of me lecturing, particularly since he asked me to talk for 4 hours in the day, 2 hours in a morning session and 2 hours in an evening session. And that's an utterly unfairly long time to submit to, you as the audience to a monologue. So I thought in both sessions, I would lay out a little bit of context, background, framework, and I'm hoping that we will be able to have a conversation. I was originally, since I didn't know how many people were going to be here, I was originally thinking that I would say, please write in the chat box. We've all gotten used to this over the past year. please write in the chat box. But since there's only 20 odd of us, either chat boxes or a raised hand will do. We can have real conversations and discussions.
Sir, one thing is I have asked all the attendees to become a panelist so that they can directly interact with each you. I think it will be a better opportunity instead of writing in the chat box.
Sure. Absolutely. No, I only meant whichever is convenient for people, please feel free to use that. I will look at the chat box and I will respond to that as well, just in case somebody has a difficulty with audio. But that's one part of it. The other part of it, biology for mankind. And the one thing, as Professor Banerjee pointed out again in his introduction, the one thing that mankind is sort of biologically obsessed with over the past year and a half is the COVID-19 pandemic caused by a member of the coronavirus family, SARS-CoV-2. And particularly from the perspective that somebody like me brings to this pandemic, having worked all my life as an immunologist, for me, how the human body interacts with a virus like SARS-CoV-2 has been a matter of professional interest and a long one. Clearly, the kind of technologies that are involved in dealing with this COVID-19 biology for mankind fall into a number of categories. You can imagine non-biological technologies. Of course, you can. You can imagine surveillance technologies. You can imagine instrumentation technologies. You can imagine socioeconomic technologies, and so on and so forth. But the core of technological interventions in the pandemic still remains biological. And that core ranges from diagnostic technologies to biosurveillance technologies to medication and related drug technologies, and of course, to vaccine technologies. So I thought what we would do over the course of the day is to begin with, let's give ourselves, all of us together, a common framework for what the epidemic is, biologically speaking, what the virus life cycle is, how the virus transmits both between bodies and within the body, what the consequences for the body are, and what the responses of the body are. Let's go from there to talking about what causes disease in the body as a consequence of virus growth in the body. And as we go along, depending on how the conversation goes, I thought we would begin to talk about the technologies that are being developed, that have been developed over the past year and a half, and that are still being developed to address questions of both evidence about what happens, as well as questions of interventions, as in, can we change what happens? And that's really how I thought we would do this. So let me, in about 15 minutes, lay out for all of us what I'm calling a common framework. So I'm not sure how many of my audience have done any after-school biology. So I'm going to take a few things for granted, but if I'm taking too much or too little for granted, please feel free to let me know, either raise a hand or in the chat box, and I will calibrate accordingly. So one of the things that I tend to begin with is that we keep referring to the ongoing pandemic as corona. And I think that this is a misnomer, that we shouldn't be referring to it like that. Part of this is simply me being pedantic. The virus is called SARS-CoV-2. Why on earth are we referring to it as corona? But there are real life implications of that difference, and I'm going to argue them for just a little while. So, is SARS-CoV-2 the virus that causes COVID-19, the disease? So, the virus is SARS-CoV-2, the disease is COVID-19. Is the virus a coronavirus? Yes. So, coronaviruses is a very large family consisting of hundreds, actually, more likely thousands of different individual virus taxa. One hesitates to use the term species with viruses and bacteria, but taxonomic groups. It is a member of the coronavirus family. Coronavirus is a family of viruses that's commonly called coronavirus because if you look at the virus particle, there is an arrangement of protein knobs on the surface of the virus particle that fancifully looks like corona. Corona is a crown in Latin, so crown viruses. So to use formal Sanskrit terminology, it is a Mukuta Vishanu Kutumbam. So the trouble is, as I said, that there are hundreds, if not thousands, of members of the coronavirus family. So when we call this particular epidemic the corona epidemic, we're actually referring to all of them. And it's a little unfair on the rest of the family to hold them responsible for the deeds of one solitary member of the family. But that aside, let's ask the question slightly differently and a little more consequentially. Are there members of the coronavirus family that we've ever met before? Or is this the first time that a coronavirus family member has come to our attention and into our awareness? And the answer is, no, this is not the first time. Okay, so were our previous experiences with coronavirus family members kind of like this one? And this is where things begin to get interesting. So in the first place, there are some common features of all known coronavirus infections in people, right? The first one seems to be, I'm saying seems to be because all of us tend to go by available evidence. If somebody finds new evidence, we will have to rewrite the story. But for the moment, all the present coronaviruses that we have encountered so far, the ongoing coronavirus is, I think, the seventh coronavirus that we are quite familiar with. So, what is common in all these seven? Let us ask that as a question. And the common thing is that all of them spread from breath to breath. They all spread as respiratory infections, which means that not just that the point of entry is the respiratory tract. They may spread, they may not spread, they may remain at one point, they may spread further down. We'll come to all that in a little while. But they enter through the respiratory tract and they are thrown out of the body via the respiratory tract into the air, and they get breathed in and infect other people. And in that sense, they are classical respiration transmitted respiratory infections. I tend to use Kabir's couplet quite commonly for this. So Kabir, of course, was not talking about no virus. Kabir was talking about his mystical God. When he said, "Khunji hove to turta miliho pal bhar ki talas mein." If I begin looking for him, I find him with only very little looking, कहे कबीर सुनो भाई साधो सब सांसों की सांस में. Says Kabir, listen, my friends, he is found in the breath of all breaths. So that's all the 7 coronaviruses that we are familiar with. This is common to them. What else do they hold in common? And it turns out not very much else, despite the fact that they look quite alike. So what's different between them? So let's look at the most familiar ones. We think that today's virus is the most familiar one, but in reality, the most familiar ones are 4 members of the coronavirus family, named various combinations of letters and numbers, that are part of an enormous list of viruses coming from various different families, all of which cause the common cold. So there are members of rhinovirus families, there are members of coronavirus families, there are members of A, B, C virus families, all of which are capable of causing the common cold. The common cold in which we have infection and inflammation of the upper respiratory tract, meaning nose and the part of the tract that connects your nose back to your throat. And that part is really what all viruses that cause the common cold infect. That's the part that gets inflamed. That's where fluid secretion happens. So the common symptoms are cough and cold, and that's basically how we treat it, the common cold. And like all the other viruses that cause the common cold, these 4 coronaviruses are circulating in communities worldwide. They come in, they cause the common cold, and you recover. And nothing terrible happens, pretty much to anybody with these 4 coronaviruses. Clearly, that's not true of SARS-CoV-2, today's coronavirus. What about the other 2? So we met one member, the 5th member, sort of the coronavirus family about 20 years ago. We meaning humanity. And that caused a disease. The disease was called SARS, severe acute respiratory syndrome. And therefore, the virus was called SARS coronavirus or SARS-CoV. And since it has now acquired a younger cousin, it's more proper to call that virus SARS-CoV-1. 10 years ago, we met another member of the coronavirus family, another cousin. And it caused, in very colonial nomenclature, it caused a disease, respiratory disease again, that was geographically named, all of which is very inappropriate. One should never use geographical nomenclature for any such things. But it was geographically named, and it was geographically named using a term that's entirely colonial. So it was called the Middle East Respiratory Syndrome as the disease, and the virus was therefore called MERS coronavirus, and therefore MERS-CoV. And between the 4 viruses that cause the common cold and the 3 viruses in this century, 3 coronaviruses in this century that cause SARS, MERS, or COVID-19, short form COVID, let us say, there is one major difference. And that is the common cold coronaviruses infect the upper respiratory tract, the nose, the back, the nasal part of the throat, the common throat, and a little bit of the trachea, the upper airway. SARS-CoV-1, MERS-CoV, and SARS-CoV-2 all cause infection in the lower respiratory tract quite well, upper respiratory tract not quite so much. And as a consequence, two different things happen. Firstly, the trivial difference that happens, that's a common feature for the disease, especially if any of you have had COVID or have relatives or friends and family who have had COVID, you'll know this. The common cold causes a great deal of dripping, a great deal of wet cough and phlegm. SARS-CoV-2 and COVID-19 causes much more of a dry cough. None of these differences are absolute, of course. There's always overlay. There's always overlap. But this causes a dry cough because the lower respiratory tract infection is much more than the upper respiratory tract infection. That's an interesting distinction. But all of these three cause lower respiratory tract infection. And as soon as you go from an infection and inflammation in the upper respiratory tract to an infection and inflammation in the lower respiratory tract, you begin to have the possibility for more serious illness as a consequence. Because the upper respiratory tract, even if it gets inflamed, even if your nose is blocked, the back of your throat is blocked, you can still breathe through your mouth. All of us have done this. You have a really bad cold, you breathe through your mouth. But what happens when the entire tubular network carrying air to your lung gas exchange points begins to be inflamed and obstructed with fluid and swelling and so on and so forth? That's when you have really serious, severe functional deficit in the functioning of the respiratory system. And this is why an upper respiratory tract infection and a lower respiratory tract infection can have quite different consequences. So that in itself is a remarkably interesting difference. Here is the other difference that has had major real-life consequences, and this one is a difference in the coronavirus members we have encountered in this century. So we've encountered SARS-CoV-1 and MERS-CoV and SARS-CoV-2. And there is one major way in, well, actually more than one, but there's a set of major ways in which SARS-CoV-2, today's virus, differs from SARS-CoV-1 and MERS-CoV in their effects, mind you. We're not talking about sequence differences and so on and so forth. We're talking about properties. So here's the difference, and let me tell you the difference as a story. So how do you discover that you have a new virus? You discover that you have a new virus capable of causing a disease when you desperately look for a new virus. You don't discover it otherwise. When do you look for a new virus causing the disease? And here I'm going to ask a question that will recur as a motive throughout the day. Supposing we had a new virus that was causing an upper respiratory tract infection, in effect, that was causing the common cold. Would we even have bothered to find out if there was a new virus involved? Would we even have noticed that there is a disease, an illness, would we have noticed anything at all? And the answer is quite possibly no. And this is to be kept in mind when people talk about what an extraordinary event this epidemic is and so on and so forth, that it's quite possible that these sorts of viruses coming from one host species to another host species and spreading on them, for all we know, happen very, very frequently. We would not notice if it didn't cause serious illness in at least some people who are infected. So when you have people who have what is otherwise obviously an infectious disease, people have fever, people are coughing, people have inflammation in the lungs, this is being transmitted because there was an ill person in the house and then somebody else in the house fell ill. All of this, it's a little bit like it walks like a duck, it quacks like a duck, it's a duck. So in that sense, you think it's an infectious agent. You look for bacteria, you look for viruses, and over the past century and a half that we've been looking at this sort of disease microbe hunting businesses, we've used very different technologies, and we may, depending on people's interest, we may want to talk about those technologies. But basically, you're looking for the unknown. The simplest way, of course, is to see if you can grow an actual infectious agent out from material, fluid, tissue, whatever, from the patients. Can you grow a bacterium? Can you find out if it's a new bacterium? Can you grow a virus? Can you find out if it's a new virus? How do you find out whether it's a new virus or a new bacterium? Once upon a time, you used to do very stepwise, careful tests to ask if it's one of the known ones. And if it's not one of the known ones, then you look more complicatedly for an unknown one. Today, in the era of omics technologies, you can simply sequence them and you can determine quite reasonably and rapidly whether it's a new bacterium or new virus. So in China, in Wuhan, in a matter of weeks, it became quite apparent that here was a sequence of a virus and that it was a new virus, in the sense that this is not a virus that has ever been recorded as causing human disease. It's actually not a virus that's been, properly speaking, recorded, although very similar viruses have been recorded. When we say it's a new virus, it's not that there is nothing similar. Of course, it's a member of the coronavirus family. It's going to have 90+% sequence similarity with lots of other coronaviruses. But it's a new virus in the sense that we've never known it to be causing disease. All right, you find the virus. So you found 20 years ago, exactly similarly, SARS-CoV-1. You found it by identifying sequences from clinical material of seriously ill people. People seriously ill with lower respiratory tract infection and inflammation, what we all commonly call pneumonia, or what physicians insist on calling pneumonitis, inflammation of the lungs. And that was true 10 years ago as well with MERS-CoV, and that was true a year and a half ago as well with COVID-19 and SARS-CoV-2. You found a new virus. It was spreading, so you had outbreaks. You could track the outbreaks. Once you knew the virus, you could develop diagnostic tests, and here's one point of technology. With diagnostic tests and the different kinds and categories of diagnostic tests. And whoever would like to, please put a bookmark there and remind me, and we'll come back to diagnostic technologies, particularly for COVID-19. We use diagnostic tests, we identify outbreaks, we can see that the outbreaks, like breath-to-breath transmission, is spreading in clusters of people who have a lot to do with each other at relatively close quarters. That's just a straightforward no-brainer. That said, you promptly start thinking about, how do we intervene? Why do you start thinking about how do we intervene? Because people are falling seriously ill, correct? And this is where people are falling seriously ill. Infected people are falling seriously ill. This is where we are going to make one major distinction that's going to recur throughout the day. And that is, infection means that the virus has grown at least a little bit in my body. And therefore, I'm infected, and I'm, in the case of these respiratory viruses, I am throwing out the virus with my breath, with my speaking, with small droplets that come out of my nose and mouth. Infection is only that. Disease is when there are consequences of infection in terms of causing functional disturbances in the body. So I begin to cough, my chest, my throat begins to choke, my lungs fill with fluid, I have fever, I have body ache, I lose my sense of smell, all of this is illness. And then you can begin to imagine more and more and more severe signs and symptoms of illness that need more and more aggressive medical intervention, and eventually some people will die. So, what became, as soon as diagnosis of infection, virological diagnosis of infection became possible, meaning that you could detect the specific virus in respiratory fluid, it promptly became possible to determine, at least very roughly, very crudely, how much illness was being caused in people infected with this virus. And this is where a major difference has become apparent between SARS and SARS-CoV-1 20 years ago, MERS and MERS-CoV 10 years ago, and COVID-19 and SARS-CoV-2 today. For SARS-CoV-1 and MERS, if either of those viruses infected 5 people, 4 of them, maybe even all 5, but certainly 4 of them, got quite sick, and maybe 1 or 2 died. That's a really, really, really high lethality at the individual level of the infection. SARS-CoV-2 and COVID-19 is quite different. If you have 100 people infected with SARS-CoV-2, I don't think even 1 dies. Even if you have 100 people who are particularly at risk of serious illness, and we'll come to what that category is later, even if you think about that, out of 100 elderly, obese, diabetic people infected, I don't think maybe 5 might die. That's hugely higher than for young people without comorbidity. But it's not everybody who's infected. In other words, at the individual level, SARS-CoV-2 is nowhere near as dangerous a virus as SARS-CoV-1 or MERS-CoV were. It's an interesting question to ask what the mechanistic basis of the difference is. And the short answer is we don't know. The long answers, scientists have long answers to questions they don't know short answers to. But the reality is that COVID-19 as a disease and SARS-CoV-2 as a virus are not anywhere near as dangerous individually as SARS-CoV-1 or MERS-CoV. So when SARS-CoV-1 and MERS-CoV began to show outbreaks and it began to be evident that these were extraordinarily lethal diseases, the world had already been looking at Ebola fever, hemorrhagic fever disease in Western Sub-Saharan Africa. And an obvious intervention response was to make a vaccine. So people began trying to make, just as they had begun trying to make vaccines against Ebola, people, and when I say people, I mean people in universities, in public sector research institutions across the world, began trying to make vaccines against SARS-CoV-1, vaccines against MERS-CoV. And like the Ebola vaccine, these vaccines were fairly rapidly developed, went through early trials, took slowly took a couple of years, and then development of vaccines stopped. And it's instructive to ask, why did it stop?
Sir, may I
Yes,
ask you
of
one
course.
thing?
Yeah.
Actually, if I understand what you have given a comparison between the SARS-1 and SARS-2, the recent corona, if I understand properly, correct me if I am wrong, as I feel what I get, SARS-1 is more.
I can't hear you.
Hello, can you hear me?
Now I can.
Yeah. What I understand, of your discussion that this corona is not a new case. It is 4, 5, or 6, 7 virus strain is there. And what you have mentioned, the SARS-1 and comparison of this COVID.
Your voice is coming in and going out, so I'm sorry, but I can't quite understand everything.
Yes, sir. Raja, sir. Hello.
Yeah, hello.
Yes, sir. Now you're audible.
Hello. Okay, now I'm audible. Hello.
Yes,
Yeah.
barely.
So, sir, my just little question is, if you compare the SARS-1 and as you were saying the SARS-2, that is COVID now, the SARS-1 is more dangerous if I understand properly. But why that doesn't create a pandemic? But this time the pandemic is there and the death, causing death, percentage of death is more.
No, it's
Why?
not. So the pandemic is there, but the percentage of death is not more. That's what I was talking about. The percentage of death is still
Yeah, you are saying that out of 1 out of 5 and 1 out of 100. You are saying this.
correct.
Yeah. So that is one thing. That is one thing. If you little make more
Yeah.
elaborate, and what is the mechanism of this COVID pandemic is infecting the body?
Yeah. So let's go back in answer to the question. Let's go back to the point I was making about vaccine development. So vaccines got developed, and vaccines were put on the back burner, both for SARS and for MERS. Why were vaccines put on the back burner? Vaccines got put on the back burner because it became something very peculiar became apparent. What was that peculiar thing? So think about it this way. If you have a respiratory infection that goes from breath to breath, and you know that here's an infection, here's an infected person, it's going to spread, what's the most obvious intervention, in formal terms, non-pharmaceutical intervention that you use? You keep a little distance. You wear masks, you use barriers, you keep a little distance. In effect, what you therefore do, what people did in small local SARS and MERS outbreaks, and what the entire world has done over the past year and a half in the COVID epidemic, is begin to adopt, better or worse, strict or lax, some measure of physical distancing. And as soon as you use physical distancing, the efficiency of the virus population in transmitting from person to person will go down. Of course, it will go down. Here's the crucial difference. For both SARS and MERS, that kind of distancing in small outbreak after small outbreak simply halted the outbreak. For SARS-CoV-2 and COVID-19, it has not halted the outbreak. It has still persisted in spreading at reduced efficiency, but it has persisted in spreading. In other words, one major difference between SARS-CoV-1 and MERS-CoV versus SARS-CoV-2 is that both of them were much more individually lethal than SARS-CoV-1 has been. On the other hand, SARS-CoV-2 has been. On the other hand, SARS-CoV-2 appears to be far more efficiently transmitted than SARS-CoV-1 or MERS-CoV. And as a consequence, what ended up happening was the outbreaks never therefore grew explosively into a pandemic for SARS-CoV-1 and MERS-CoV. And that, if you like, is my response to your question. That here is a major difference between SARS-CoV-1 and MERS-CoV on the one hand and SARS-CoV-2 on the other hand. As a consequence, physical distancing simply pretty much completely controlled outbreaks of those two viruses to the point that that local outbreaks never grew into a pandemic. On the other hand, that has clearly not been sufficient. It has been effective, but not sufficient to shut the pandemic down for SARS-CoV-2 and COVID-19. As I said earlier, let me simply reiterate. Do we know what the differences are that are definitely responsible for either of these characteristics? In other words, why is it that those two viruses are much more individually capable of causing severe disease than SARS-CoV-2 is? On the other hand, SARS-CoV-2 is much more easily apparently transmissible despite physical distancing than those two have been. And we have guesses about what immune modulations they have that today's virus doesn't, and what the affinity of the spike protein of today's virus for cellular receptors is that those viruses may not have. But none of that has been, properly speaking, robustly and rigorously supported with good evidence at the moment. So at the moment, we don't know. But the fact remains that there are these differences. And as a consequence, two things happened. One, we didn't have pandemics of SARS and MERS. But two, we had vaccines developed and tested to some degree against SARS and MERS. And last year, when it became quite apparent that simple physical distancing and related care in reducing transmission were not halting SARS-CoV-2 in its tracks, unlike the earlier viruses, it was quite obvious to everybody that one of the things that was this time likely to be necessary was vaccination. So what did people do? People essentially took up all the road-tested, partially tested vaccines, vaccine designs, and vaccine platforms that they had developed for Ebola, for SARS, for MERS, and particularly for SARS and MERS, because this is a member of exactly the same family. So all you need to do is to tweak the vaccine a little bit, put it back into trials. You already know what kind of preclinical trials you want to do. You do those very rapidly and you can go into clinical trials. And that's how, in a matter of months, we've had vaccines against SARS-CoV-2 and COVID-19. So the vaccines are not some miracle of science and technology. The vaccines are, today's vaccines are living real-life evidence that if you're not getting options to unmute, please feel free to write in the chat box and I will respond, although it would be nice if unmuting was possible. But I'll respond to comments and questions quite happily, even if you write. So a consequence, therefore, is that this is cumulative, like pretty much all other science and technology that all of us are familiar with. We've been doing this stuff for a long time. These are platform technologies. And again, vaccine platform technologies is something that I hope to come to at some point during the day. These vaccine platform technologies have been in development for quite a while. All the present vaccines, the NIH Moderna mRNA vaccine, the BioNTech Pfizer mRNA vaccine, the Oxford AstraZeneca, Serum Institute of India, Covishield adenoviral vector vaccine, the Gamaleya Institute adenoviral vector vaccine, and all the Chinese vaccines, which range from inactivated virus vaccine like the Bharat Biotech Covaxin design to adenoviral vector vaccines, to protein vaccines such as Novavax's vaccine. All of these technologies were technologies that were partially road tested against these earlier members of the coronavirus family, as well as against other viruses such as Ebola. And that has been a core reason for how we have responded rapidly. So the rapid response is not a miracle of targeted research, so-called targeted, relevant and applied research. The rapid response is evidence that the broad front of integrated research in science and technology builds cumulative enabling for rapid responses to extraordinarily novel new risks and dangers. And that's a lesson that all of us should keep in mind when we, as practitioners of science and as practitioners, as teachers of science and technology, talk to our societies and our communities about the value of research in science and technology. That said, let me take a step back. Are there questions? Because it seems to me that if all the attendees were panelists, they would be able to unmute themselves and ask questions. Okay. So let's take one step back and now think about the mechanics of transmission, and that in the context of this very recent in the news debate about does the virus spread through air or not, and how finally the WHO has acknowledged that it spreads through air and so on and so forth. And in order to do that, let's think about what's actually happening. The cells lining my respiratory tract, many of them are infected with virus. We'll come back to the biology of virus infection in a little bit, but the cells are infected with virus, and therefore they're shedding virus into the fluid that lines my respiratory tract. So when I talk, I laugh, I cough, I sneeze, I shout, I sing, whatever. There are always droplets coming out of my nose or mouth, right? And the sizes of these droplets are extremely variable. You can have really, really large, easily visible to the naked eye droplets that don't travel very far, that fall down fairly rapidly. Everybody in real life classrooms is familiar with this somewhat uncomfortable reality of life. And the smaller the droplet becomes, so there's a range of droplets. So the infectibility is not more, is more in SARS-CoV-2 compared to SARS-CoV-1 for reasons that I am repeating myself. We really don't know well enough. The simple argument that is being made is that the SARS-CoV-2 spike protein affinity for ACE2 receptors on human cell surfaces is much greater. Even that is a little bit debated, but in any case, it's not absolutely certain that that's the reason for the better transmissibility. I would rather not use the word infectibility. The better transmissibility of SARS-CoV-2. Young persons are not dying of COVID-19 in high percentage. So, but that's something that, if you will allow me to defer, we'll come back to when we begin talking about differences between COVID-19 characteristics last year versus COVID-19 characteristics this year, and whether there are real differences or whether we are only seeing apparent differences because of the massive difference in numbers between last year and this year. So that's really going to be the point, but we'll come back to that a little more extensively as we go along. So we're talking about droplets. So if there are virus particles in the fluid, then every time droplets come out of my nose or mouth, those droplets are going to carry virus particles. And the payload, the number of virus particles per droplet, one of the factors determining the number is, of course, the size of the droplet. That large droplets are going to have a much higher payload of virus particles, all other conditions being the same, whereas small particles are going to have much smaller numbers. So here's the difference. If I'm sitting very close to somebody, I am likely to I'm quite happy to simply take questions as they arise, but then we are not going to do any systematic discussion, because these are questions for each of which I will need to do a large amount of background. So different mutant varieties of SARS-CoV appear within a year. Why do they appear? That's a question that requires explaining a great deal of biology. It requires explaining viral biology, because it requires explaining what the difference between RNA copying versus DNA copying is. It requires explaining a certain amount of evolutionary biology, and it requires a discussion on the evidence of what the properties of these mutants are. And if I'm quite happy to go into that, but if I go into that, then this, what I'm calling general systematic background, is going to be left behind. So is it because only of RNA virus or different human race genome? There is no evidence whatsoever about different human race genome. In the first place, there is no evidence for human races in any deeply biologically meaningful fashion. There is evidence of some genetic predilections with population bottlenecks, but not at racial levels. Diverse climate in India or anywhere else has not been shown to be a factor so far definitively affecting COVID-19 patterns anywhere in the world. Symptoms are varying from person to person in pretty much every disease you can think of. So it's not simply a matter of symptoms varying from person to person in COVID-19. Symptoms vary from person to person, and we'll talk about what the package of symptoms is and where it comes from. But can biologists explain why person X suffering from cholera versus person Y suffering from cholera have somewhat different symptoms? No. Person X suffering from typhoid fever versus person Y suffering from typhoid fever can have quite different symptoms. In fact, can have radically different symptoms. We don't really have any way of explaining individual differences at that level at the moment. All we can say is, here's a group of symptoms, and some people may have a little more of this, a little less of that, and vice versa, and so on and so forth. So the rest of it I will come back to in just a little while as we go along. So here's, to go back to my problem with transmission, droplets. So I'm sitting close to somebody, and they are infected, and they're talking to me, and a big droplet, relatively large droplet, not really visible, but still a relatively large droplet, comes, and it would have fallen to the ground within 2 or 3 feet, but I'm sitting at really a couple of feet distance, so it goes directly into my breath. I have therefore taken on a very large viral load in one droplet that's going to land pretty much in one place, in one location, in my respiratory tract. So that's a problem, right? Because it's infecting me with a higher dose of virus, and it's infecting one specific location. On the other hand, if I'm sitting at a distance, these large droplets are not a major risk for me. But imagine what happens with small droplets. So small droplets, you have okay, what is the technique of extracting virus for doing sequence analysis? Really, this is Googleable. What you do is, because the virus has a protein coat, you digest the protein coat. So you have fluid, nasal sample fluid, in which there are virus particles, presumed virus particles. You digest the protein coat with proteinases, and you get the viral RNA, and what you use is RNase inhibitors, so that the released RNA is not digested. And that's really the principle of how you extract not virus, but viral RNA directly. And then you can actually extract the viral RNA in some technologies, and in other technologies you can simply use the fluid to amplify, to convert the RNA into cDNA, and then to amplify the cDNA for the quantitative real-time polymerase chain reaction test. So under these circumstances, what you have is very small droplets that are accessible to a person, that have access to a person sitting far away. But the amount of virus per droplet is much smaller. But here's what might happen. If you're sitting in an air-conditioned office with multiple rooms, all of which are being cooled by the same recirculating central air conditioning air handling unit, then the small droplets from me are going to get pulled in and are going to get distributed all over the building or all over the set of rooms where that air handling unit is functioning. And as a result, because this is happening over and over again, you can imagine a situation where individually small payload droplets, but in very large amounts, because of repeated over and over pumping of air, prolonged exposure, are getting into the airways of people who are sitting in another room. And these are two very different models of virus transmission that will be more or less important depending on circumstances. So if you're sitting outside, outdoors, where there is a breeze going and small droplets are simply going to dilute out, then small droplet-based transmission may not be a major issue. Big droplet-based transmission may be a major issue. On the other hand, if you're sitting indoors in an air-conditioned situation, or in a heated air situation, such as in temperate countries, then of course, the so-called aerosol transmission of very small droplets would become a major issue. The interesting thing about the small droplet versus large droplet is also another thing, that if I have 1,000 small droplets versus 10 large droplets, those 10 large droplets will go and sit in 10 locations in my throat or my trachea or my bronchi. But the 1,000 small droplets will go and sit in many more locations. And we haven't so far figured out what the distinction is between these initiating lesion location numbers as far as causing disease is concerned. It's not an easy system to investigate in controlled fashion. So people have thought about it, but people haven't really done interesting experiments with it. However, let us consider what happens when virus lands. More correctly, a droplet lands in fluid that is covering the wall of the throat, the trachea, the bronchi, and so on. And virus particles, keep in mind that virus particles are metabolically inactive. There is no biological process going on in the virus particle. There is no energy being utilized. There is no enzymatic activity actually going on, and so on and so forth. So in that sense, the virus particle is kind of non-living. That's important for intervention purposes, because if you damage the virus particle by stripping away its lipid, by using detergents, for example, or by damaging its cell surface protein conformations by using 70% alcohol, for example, or by proteases that are present, protein digesting enzymes that are present in pretty much all body fluid to some extent or another, proteases that will begin making nicks in the viral protein coat, the virus particle, unlike a bacterium, has no way of repairing itself. And therefore, the virus particle, infective virus particle, has a relatively short half-life. It's going to remain infectious only for a relatively short period of time, whereas bacteria will remain bacteria. They are metabolically active. They will scrounge energy from some, they will scrounge complex carbon sources from somewhere around them, and they will grow. And therefore, if you damage them, they can, to some extent, repair damage. So that's a major distinction. And that's why the longer you prevent a virus particle from sticking to a cell and infecting it, the more likely it becomes that that virus particle is going to be rendered non-infectious in a fairly short while. And this becomes a major component of antiviral defense. So when you think about it in those terms, the virus particle sinks through fluid. It begins to meet all the proteases and stuff that's all around. So it has, as I said, a fairly short time window before it binds to cell. So if it just comes and sits on a cell, that's not strong enough binding. It's going to be jiggling and it's not going to get taken up and nothing is going to happen. If it binds very tightly, and that can only happen with complementary protein-protein recognition interactions, non-covalent protein-protein interactions, then you have extremely strong, stable binding, and that stable binding, either accompanied by uptake, for SARS-CoV-2 accompanied by uptake into the cell, allows the virus this stable synaptic interface through which it can transfer its RNA into the cytoplasm of the cell. And once it does that, two separate sets of biochemical processes begin. The first is the obvious viral biochemical process. It's a viral mRNA. It begins to use cellular machinery to make viral proteins, early proteins, non-structural proteins, which modulate cellular behavior and begin the process of takeover of the translational machinery for virus protein building, for virus RNA copying to begin, and then finally for assembling virus copies. And from one virus particle coming into one cell, you can have hundreds, actually thousands of virion particles emerging from that infected cell. This is an important difference between a virus infection and a bacterial infection, because bacterial infection, bacterial growth goes from 1 to 2 to 4 to 8 to 16 to 32 to 64 to 128 to 56 and so on and so forth. Virus growth in principle can go from one virus particle coming into a cell, giving rise to 1,000 virus particles, 1,000 virus particles going into cell, therefore giving rise to 1,000,000 virus particles, and so on and so forth. So the numerical trajectories of virus growth and bacterial growth are quite different. And that is something that needs to be kept in mind when we think about the radical differences between how clinically useful antibiotics are for bacterial infection versus how much more limited the clinical utility is of antivirals in viral infections. Remdesivir, the entire saga of remdesivir being one example. So let me address the question of what is the chance to be infected from surface contacts. So that's a good question, and I should have really referred to that, and I didn't. So here goes. So as I said, large droplets come out and fall down onto surfaces. So I can therefore, in principle, put my hand on those droplets, or when they dry on the little crust, and then I can touch my nose or mouth with it, and I can therefore, in theory, do this indirect transmission of virus. There are limiting features. Those limiting features are, number one, remember that the fluid that is coming out of my mouth or nose already has proteases and stuff like that. So the virus is not having the virus particle is not having an easy time of it in the particle. In the droplet. The droplet falls down, the droplet begins to dry. Depending on, so different viruses have proteins that are differentially resistant to dehydration, but a completely dry virus particle may also lose protein conformation and therefore become non-infectious. So it's quite possible that you will detect viral RNA in those particles for a fairly long time to come, but whether any of those particles is truly capable of causing infection remains completely unproven. So ever since last March, a huge number of papers have come up that have studied exactly this. How long does virus survive on surfaces? And the problem is, number one, how long a virus survives has two different kinds of answers depending on whether you're looking for whether infectious virus survives or whether detectable virus survives. And pretty much universally, 95% of papers actually simply look for detectable virus, not for infectious virus. In fact, I can think of only a couple of papers last year that carefully looked at infectious virus survival. Infectious virus survival is always going to be much more short duration than detectable virus survival, number one. Number two, the duration for which virus remains detectable is also going to be a function of how much virus there was to begin with. And that's going to show an enormous amount of variation. So there isn't an easy answer to how significant is indirect transmission. So it's only under very specific accidental controlled situations and circumstances that people have been able to study sort of examples of indirect transmission. And the general consensus, so far as current understanding goes, is that the contribution of indirect transmission from surface contact, like these kinds of surfaces, is less than 5% of the total transmission of SARS-CoV-2 during the pandemic. So, does it never happen? No. Of course it can happen under appropriate circumstances. It can certainly happen. There are examples, for example, of people visiting patients' rooms when the patient was not in the room, and of having picked up phone or something or the other, and then having left before the patient came back from out of the toilet, and having gotten infected. So is it anecdotally possible? Yes, it is. Is it highly likely? No, it is not. What is the empirical evidence? As I said, the general epidemiologist's consensus is that less than 5% of all transmission seems to be indirect transmission of this sort overall. So do I think that vegetables and grocery packets are an easy source of infection? No, I don't think so. Am I going to say, oh, it's not at all likely? No. You'll always have some examples, especially during a pandemic when the number of cases is so extraordinarily high. If we look hard enough, we will always find examples of pretty much any of these kinds of transmissions. But none of them is a particularly high likelihood transmission. And the really important point is, why isn't it a high likelihood transmission? Is because of these variabilities of how much virus falls down in one place for you to pick up, number one. Number two, how much actually infectious virus survives, rather than just detectable viral RNA can be found, how much truly infectious virus survives over time. The question of what is the probability of getting infection in air travel, even if one has 2 masks on. Air travel has been a matter of concern throughout the pandemic, primarily because, as you can imagine from my description of small droplet recirculation-based transmission between rooms, an airplane is an obvious place where air is being recirculated over and over. Now, in theory, we are supposed to be using filters in all of these. The question is, what is the exclusion limit of those filters? Is it 5 micrometers? Is it 2 micrometers? Is it 1 micrometer? As you make the filter smaller and smaller, you need higher and higher energy for running the air recirculation system. You also need filter replacement at an extraordinarily high rate. So airlines also tend to do a little bit of cost cutting in all of this. And as a consequence, what airlines have said is that they are using an appropriate, I think below 2 micrometer, although somebody might want to fact check me on that, droplet exclusion. But all of that as all of you are aware, is a statistical concept. In other words, if there are 20 asymptomatically infected people on the flight, and there is therefore a huge amount of virus being put out in extremely small droplets by a large number of people, then even if 99.9% of it is removed, the residual, simply because there was a very large amount to start with, may be enough to infect a few people. So air travel does pose risks. However, do keep in mind that what we are talking about is the statistical probability of exclusion of droplets by one filtration system after another filtration system after another filtration system after another filtration system, such as the example with 2 masks on that you've written in the chat box. And as a consequence, I think that with current precautions, with the current regulations demanded of airlines, I have yet to see any evidence that air travel has led to, in this calendar year, has led to major outbreaks. Last calendar year, before all of this became stringent, I have heard of air travel-based small outbreak clusters arising, but I haven't heard of one this year. So that's as much as I can tell you about air travel transmission in particular. So let's go back to our initiation of disease. So what happens? We've got viral RNA introduced into a cell locally, and the virus is going to start assembling copies and so on and so forth, and it's going to start releasing copies out of the cell, initially without completely rupturing the cell, but the cell is sick because cellular machinery that's important for maintaining cellular life turnover has been repurposed and directed towards viral synthesis and assembly, and therefore the cell is going to become sicker and sicker and sicker, and eventually the cell is going to die. But by that time, a lot of virus particles will have been released. But here's the interesting thing that happens. So double-stranded RNA virus, so double-stranded RNA comes up as naked RNA into the cytoplasm of the virus. Now, the cytoplasm of the virus is not a place to be finding double-stranded RNA in normally. And this is a principle of immune sensors in general. Immune sensors circulate in the cytoplasm of cells, pretty much all cells, looking for the secondary structures of double-stranded RNA or DNA, neither of which should be found naked in the cytoplasm. And if they are found naked in the cytoplasm, then in an evolutionary sense, a presumption can be made that this is some potentially infectious stuff that is where it should not be, and therefore there should be a response. And over evolutionary time, therefore, downstream of a sensor for things like double-stranded RNA, there is a whole signal transduction mechanism that has evolved that gives rise to 2 functional outcomes. One functional outcome is type 1 interferons that are released locally that allow cells to resist viral takeover using a variety of ways. And a second of similarly secreted molecules that mediate 2 categories of functions. One, they begin to build a containment zone in place so that you're basically containing infection at that anatomical location. And they begin to induce the recruitment of specialized cells of the immune system into that location. And this is important because I would like everybody to keep in mind a general principle that we arrive at here. And that is, we want immune system activation at the microanatomical location where infection is present. We don't want it everywhere. And I'll come to why we don't want it everywhere in just a second. So this is the initial immune response that all cells of the body have. It's an immune response that depends on viral nucleic acid entering cells, because that's where the sensor is. And therefore, the immune responses begin after the viral RNA has entered cells. And this is therefore just a little bit late, because in this sense, you can imagine that some amount of virus infection has happened, some amount of new virus progeny production is going to happen, regardless of whether the type 1 interferon and the inflammatory pathways are adequately triggered and whether they adequately function or not. However, once you recruit specialized cells of the immune system, then you induce yet another component, because these specialized cells of the immune system, some of them, will carry virus to local lymph nodes, so lymph nodes in your neck, lymph nodes inside your chest, and so on and so forth, where a whole different adaptive immune response will take place. And the principles of recognition differ. So keep in mind that the principle of recognition with the initial immune sensor, for example, viral nucleic acid, was simply the secondary structure of viral nucleic acid. And therefore, that sensor would not distinguish between SARS-CoV-2 RNA versus SARS-CoV-1 RNA versus MERS-CoV RNA versus influenza RNA, versus any other viral RNA. And that is what we generally call an innate immune response that depends on these very broad structural molecular recognition motifs for being triggered. On the other hand, the adaptive immune response that's triggered by the immune specialized lineage cells that come in or are already there and that carry virus to the local lymph node and initiate an immune response there, is viral structure specific. Structure specific in terms of peptide sequences as far as T lymphocyte responses are concerned, structure specific in terms of three-dimensional topographies, molecular topographies, as far as B lymphocyte responses are concerned. So at that level, we've got three different responses that are interlocking. One obvious response is that we make antibodies. And antibodies are simply B cell receptors that recognize viral cell surface molecular topographies and that begin to secrete the receptors. And the secreted receptors are essentially what we call antibodies. So you have antibodies that will circulate in body fluids and that will bind to viral particle surface molecular targets. Now keep in mind how the virus enters cells. Whether the virus is entering cell at first entry or within the body from one cell to another, what the virus does is use its spike protein to bind to ACE2 on the cell surface. ACE2 as a receptor is fairly widespread in the body, and therefore, even though the virus SARS-CoV-2 enters the body through the respiratory system, it can eventually, given enough opportunity, infect many cells and organs in the body through ACE2 binding. But if you have circulating antibodies that bind to approximately the same site, approximately the same molecular topography of spike protein through which the spike protein binds to ACE2, then you are basically capping the spike protein and you are preventing it from binding to ACE2. Basically, you're preventing the viral particle from engaging with a cell. And as I said a little while back, if you prevent the virus particle from getting in quickly, then eventually the virus particle is going to become non-infectious because proteases and so on and so forth are going to damage it so much that it simply won't function as a virus particle. And as a consequence, this is how neutralizing antibodies, so you neutralize virus binding to cell surfaces, and those are neutralizing antibodies. But you can also make antibodies against various other components of the virus that don't really affect spike binding to cell surfaces, and therefore those are not neutralizing antibodies. In fact, because antibodies bound to viral particles have tail domains to the antibody protein, which themselves can be recognized by specialized cells of the immune system. You can actually imagine that some antibodies may in fact promote uptake of virus particles by cells of the immune system. And for example, in dengue hemorrhagic fever, you can therefore have antibody dependent enhancement of disease. It's something that all viral immunology biologists worry about with antibody responses. So far, I hasten to add, there has been no evidence of antibody-dependent enhancement in SARS-CoV-2 and anti-SARS-CoV-2 antibodies. So far. That doesn't mean that we won't find examples, but so far we haven't found them. We haven't found them in either antibodies in response to natural infections or in antibodies in response to vaccines. So that's antibody-dependent enhancement, and that's how antibodies work. Do non-neutralizing antibodies have other functions through which they contribute to antiviral functionalities? That's possible. We don't know, particularly with SARS-CoV-2 and COVID-19, we don't know if they are, or if there is any such evidence or not. CD4 T cells and CD8 T cells, two different categories of T cells, are also triggered, and as I said, they recognize peptide sequences on surfaces of infected or virus processing cells. And what CD4 T cells do is contribute to amplifying the inflammatory process on the one hand. So they contribute to the sort of local microcontainment zones of inflammation on the one hand that allow localization of infection and prevent the infection from spreading throughout the body, number one. And number two, CD4 T cells are also important for the B cell antibody response to mature into a high potency, high magnitude response. CD8 T cells, on the other hand, can recognize virus-infected cells and can kill virus-infected cells. So, in a sense, they abort viral infection at the individual cellular level. To what extent are CD4 and even more CD8 T cell responses, again, whether generated with natural infection or generated with vaccines, critical for providing protection against disease or protection against infection and transmission? We don't know as yet. There is evidence in other diseases, in other vaccines, that these responses help, but for the moment with SARS-CoV-2, we don't know. We have all sorts of speculations, we have all sorts of very vague indicative evidence, but we don't know with any certainty. We do know that neutralizing antibodies do protect against severe infection. We do know that they protect against transmissible infection. And all of that we'll come to as we talk about vaccines, probably in the evening. Let's talk about symptoms. So think about what happens in the location where virus is growing, where immune responses have kicked in, where therefore inflammatory pathways are trying to build a microcontainment zone, where the locally growing virus is kept contained. All of this is a matter of hours to days. The virus is being kept contained and specialized cells of the immune system are being recruited. And as a result, what happens locally is that the local blood supply is re-engineered, and therefore there is swelling, there is oozing, there is a lot of other cells of the immune system that are coming in, so the place gets very crowded. All in all, local functionality is almost certainly going to be affected. So it is the antiviral response of the body, effectively, it is the immune response that is causing local dysfunction. Is the virus causing local dysfunction? Of course it is, because the virus is growing in cells and those cells will eventually die. And when cells die, lining cells die, the lining will be denuded and you will therefore get some symptoms. But because these early innate immune responses are kicking in place fairly rapidly, even before major virus expansion happens and lots of cells die as a consequence of the virus, the immune responses themselves have actually begun to cause symptoms. And it's always this combination of virus and immune response that's causing tissue dysfunction. Malfunctioning of tissues locally is being caused quite extensively by the immune response, by the inflammation, by the swelling that is generated by the inflammation, which is going to cause irritation and cough. Just as much as virus mediated cell death and denuding of the lining is going to cause irritation and cough, the swelling is going to cause irritation and cough. The swelling is because the hemodynamics locally are reorganized. You have a lot of fluid oozing. Now, if fluid is oozing in my nose or my throat, I can simply sneeze or cough it out. But if fluid is oozing further down in my lower respiratory tract, then it begins to accumulate in the air sacs of my lungs. And if fluid begins to accumulate in the air sacs of my lungs, then oxygen and carbon dioxide exchange, which depends on there being an extremely thin film through which the concentration, the diffusion gradient for oxygen this way and carbon dioxide that way gets established, is utterly disrupted because there is now an enormous fluid dead space, which is now hindering oxygen and carbon dioxide exchange. And when that happens, my body begins to run short of oxygen, my pulse oximeter oxygen tension begins to drop, I have what is effectively a viral pneumonia, which is what is being detected as fluid in the lower respiratory tract and in alveoli, which is what the so-called famous HRCT score is. HRCT simply stands, I think, for high resolution computed tomography, which is really just a fancy X-ray. And the fancy X-ray can quantify for you just how much opacity, meaning fluid, there is in the lower airways and in the lung air sacs. And all of that is, all of it is caused as a disturbance by the immune responses to the virus. Going forward, remember that local inflammatory responses are set up as containment zones. And in order to do that, the standard biological system designs, are to use secreted soluble molecules that have a very short radius of action and therefore that act only locally. And you think, hey, that's great, except that these are biological systems. No containment is 100%. So there's always a little bit of spillover from each location of inflammation. Now, if I have 100 locations of inflammation, a little bit spills over from each one of these and goes into general circulation. It adds to each other, but it still doesn't reach very high circulating values. But if I have 5,000 locations of inflammation all over my lungs, then the stuff that overflows from each one of these adds to each other, adds to the stuff that's overflowing from other locations in general circulation. And what ends up happening? What ends up happening is that these circulating mediator protein molecules, cytokines and chemokines, reach, even though they are supposed to be short radius of action, locally acting biological mediators, they end up reaching concentrations in general circulations that are above threshold. And once that happens, they begin to cause body-wide inflammation. And when that happens, we are in dire difficulties because now we have inflammation going on everywhere in the body, regardless of where the infection is. The infection is still in the lungs and so on and so forth, maybe a couple of other places in the body. But because there is an extensive amount of inflammation, perhaps because incoming infection dose was very high, especially was very highly distributed, perhaps because the initial innate responses causing containment began kicking in place just a little more slowly and therefore allowed the virus to spread to many more locations before inflammation truly began. For whatever reason, What we now have is the virus being brought under control? Yes, the virus is being brought under control, but it's being brought under control in so many different locations that spillover from those locations has now triggered a body-wide systemic cytokine storm. And that's when patients become really severely ill. And you can now imagine why it is that for such patients, for such severely ill people, what they really need is to stop the cytokine storm from acting in places in the body where there is no virus. And that's why inflammation suppressing therapeutic interventions become important technologies for these severely ill patients of COVID-19. Are their bodies finally dealing with the virus? By and large, yes. There are exceptions to that in a very small handful of cases where the virus is apparently growing extraordinarily widely in the patient. But most of those people are truly immunocompromised individuals, either people who are genetically suffering from immunodeficiency syndromes or who are suffering from infectious immunodeficiency syndromes such as HIV/AIDS, or who are undergoing cancer chemotherapy and are dealing with chemotherapeutic drug regimens that suppress the immune system, or are people suffering from chronic autoimmune diseases and are receiving immunosuppressive therapy and are therefore immunosuppressed. Otherwise, for the bulk of people who land up with severe COVID-19 in critical care, it's because they have these extremely strong immune responses ongoing. And the trick there in therapy is that these immune responses are important because they're dealing with the virus. So you suppress them too much, you're allowing virus growth. On the other hand, the immune responses are causing damage. They're causing local damage in the lungs. And for that, you need to support lung function. You support it by high tension oxygen. You support it by ventilators. And at extreme situations, you support it by therapeutic interventions like the ECMO interventions. ECMO is extracorporeal membrane oxygenation. Effectively, you pass the patient's blood through a lung machine, through an artificial lung machine, where oxygenation is provided. So you can do all that and the lungs will recover. They will control the virus. The immune response in the lungs locally will control the virus, will bring down the virus load, the inflammation will die down, and the patient will recover. Eventually, lung functions. You got to keep the patient alive till then. But in addition to this, the byproduct inflammation that's going on throughout the body is causing multi-system, multi-organ failures by inflammation in the body. And this misplaced consequence of inflammation also needs to be controlled. And it's... Is that a question? Yeah. So that's going to be a problem, and that requires immunosuppression. So the therapeutic trick that real-life intensive care units are always dealing with is how much of immunosuppression to do so that you can control the body-wide inflammatory response and get other organs to recover and be protected, yet not repress the immune response so much that locally, where the antiviral response is going on, you don't simply allow not simply the virus, but because there is all sorts of fluid accumulated and so on and so forth, you have other opportunistic microbes beginning to grow. And those opportunistic microbes include bacterial infections of bacteria with ordinarily low virulence, which don't cause disease, but which can begin to cause disease. Pseudomonas bacterial secondary pneumonia being a very common example, for which then you will need to use antibiotics. And if those are acquired during hospital stay, then the bacteria can very easily commonly be antibiotic resistant, and therefore you have a whole new set of difficulties and problems in treatment. And in the upper respiratory tract, if you have immunosuppressed with steroids way too much, then you have problems like mucormycosis, like aspergillus, fungal infections like mucormycosis, aspergillosis, candidiosis, and so on and so forth. So therapy is always going to be a bit of a balance. And in this therapy of severe disease, because the body by and large is gaining control of viral growth all by itself, antiviral drugs contribute only modest benefit. It's not that they don't contribute clinical benefit, but they do not contribute clinical improvement as dramatically as antibiotics do in bacterial infections. And you will remember my reference, whatever, a year, hour and a bit ago, about how the difference in the growth trajectories, in the numerical growth trajectories of viruses versus bacteria may be a contributory feature for explaining this difference between antibiotics versus antivirals as clinically useful. This is why remdesivir works most strikingly in early stages of infection. Within the first couple of days of acquiring symptoms, if remdesivir begins to be given, this is very hard because at that point, most people have only mild to moderate disease. There is no real reason to admit them to hospital, yet remdesivir needs to be given intravenously, and therefore this is all a major practical problem. This is one of the reasons why the antiviral technologies that we should be aiming for are technologies that can be taken orally and that can be cheap enough to be available quite extensively, because they should become available to everybody to take as soon as they have symptoms, because that's when they are going to be most useful in controlling virus load, which will have both the individual result of protecting the individual from severe illness possibility and a community consequence, because it will reduce the amount of transmission of virus that that individual achieves. So this is the trajectory of the virus infection. What we are going to do in 5 minutes more is set up for ourselves the consequences of recovery. And we're going to talk about two kinds of consequences. One is the consequences of symptoms and signs, long COVID, in other words. And the other is the consequences of protectedness, resistance to reinfection, in other words. So let's talk about long COVID first. Clearly, if you have a great deal of inflammation in the lungs, if you have a great deal of tissue damage elsewhere, with neurological damage, with kidney damage, with vascular damage, then complete recovery may be slow, taking weeks and weeks and weeks and weeks and weeks, and may leave scarring behind, because recovery from inflammation will mean tissue repair, and tissue repair can quite frequently lead to scarring. And as a consequence, there may be long-term consequences of the short duration acute disease that COVID-19 normally is. We don't understand all of long COVID. Long COVID has a list of 50, 60 symptoms. I mean, you think that short COVID has variable symptoms. You should see those friends of mine across the world who are looking at long COVID in their clinics. There is an extraordinary diversity of symptoms. How much of that diversity is because once the virus gets into the body, it can infect many different lineages, because ACE2, the receptor protein, is present on many different cell lineages. How much of it is because the cytokine storm has caused local inflammatory damage in many organs, and in every long COVID patient, the organs more or less affected are a little bit different, and therefore symptoms are different. We really don't understand long COVID well enough to be able to answer any of these questions. And as a matter of fact, one of the long-term consequences of the COVID-19 pandemic is going to be that for many years to come, we are going to be dealing with a specialty of long COVID clinical treatment. and trying to understand different categories, different subgroups of long COVID, and trying to help them the best, most optimized way we can, is going to be a long-term commitment of healthcare systems. So that's about long COVID. But think about what I said, that the virus comes into my body for the first time, it grows, my immune responses kick in, my initial immune responses simply recognize a virus. They don't recognize SARS-CoV-2. They're simply saying, here's double-stranded RNA, we are going to respond, we are going to make antiviral type 1 interferons, we're going to make inflammatory cytokines, we are going to build microcontainment zones locally, we are going to invite cells of the specialized immune system to come in and to do their stuff. And their stuff is antibody responses, CD4 responses, CD8 responses. So you can imagine that virus load goes up. Along with that, with a little lag, immune responses go up. Initially, it's only innate immune responses. Steadily, it becomes the adaptive CD4, CD8 B cell responses. Virus load begins to come down. The activated immune system cells begin to calm down, begin to settle back to baseline. At that point, what we are left with, the virus is eliminated, there is no active immune response going on. What we are left with is two things. We are left with an increased frequency of T cells and B cells, memory cells, specific to various components of this particular virus. And we are left with a bunch of cells that are sitting in our bone marrow that are constitutively simply cranking out antibodies. And therefore, we are left with long-lived antibody-secreting cells in the body that are secreting antibody, and therefore we are left with antibodies that are circulating all over the body, and to a certain extent, depending on the nature of those antibody responses, are found in secretions as well as secretory antibodies. Now, as the final point, and I'm hoping that with this long introduction, we can segue in the evening to vaccine technologies, vaccine evaluation, and I hope vaccine myths and realities about COVID-19. So what we are now left with is, let's say I have caught an infection, I've gone through all this process, I have recovered, I'm healthy. New exposure happens. Virus droplets come in. The first thing that's different is in my body fluids, including in my respiratory fluids, is now you have antibodies. And some of these antibodies are neutralizing antibodies, meaning antibodies that actually cap the spike protein so that they don't let the spike protein bind to ACE2. And therefore, the circulating neutralizing antibodies provide me a pathway. It depends on their concentration, it depends on their affinity and potency, but they provide me a pathway with, in principle, preventing incoming viruses from establishing any infection at all, any cellular infection at all. And that is a property that only circulating antibodies, particularly circulating antibodies in secretory fluids, have. T cells cannot do this because for T cells to be stimulated, cells must first be infected with the virus, at least a few cells. That's when T cells get stimulated. They'll do all sorts of useful things, but they're not going to do what circulating antibodies in secretory fluids are going to do. Those best are, sorry, was there a question? No. Those at best are going to actually prevent any infection of cells at all from happening. And you can therefore imagine that this is thought of as generally a very good thing, and everybody likes to shoot for this. Whether they succeed or not, we will talk about in the evening, but that's basically what we are talking about. Keep in mind, however, that if such a reinfection does lead to some limited amount of virus growth, all my memory cells, my memory B cells that are now capable of responding by making huge amounts of pretty potent antibody. My memory CD4 T cells, CD8 T cells that are capable of building very quickly, building inflammatory containment zones that are capable of identifying and killing virus infected cells are also going to kick in, and therefore are more than likely to cause a relatively short-lived, small magnitude abortive reinfection of the virus. And this is how a first infection by the virus will protect me from subsequent infections, will protect me even better. This is not to say that I was not capable of an immune protection against the virus the first time around, but the second time around, it's even better. And you can now imagine where we will go with this background into the technology of building, evaluating, and using vaccines in real life. So the question, will virology emerge as a new subject of study like nanotechnology? I'm afraid my friends who are virologists will find that a deeply depressing question, because it is their understanding that virology has been a subject of study for a very, very long time. They've been virologists for a very long time. In fact, they've been warning us, warning the world for a very long time that you are not paying enough attention to viruses, particularly to respiratory viruses, because they have the capacity to develop into pandemics, and therefore we should be paying even more attention to them. I suspect that we will be paying much more attention to virology going forward from here, but I doubt that I would call it a new field of study. So I will stop there. I have gone for almost 2 hours, and if there are questions, I was hoping that there would be more questions, but if there are end questions, I'm happy to address those. And if there are not, then lunch calls for everybody, so we can stop here. Thank you all very much. I'm astonished that all 20, 25 people have stayed online looking at me talking for 2 hours. So specifically, thank you all very much.
Thank you, Professor Roth, for a nice illuminating talk. I hope I am audible.
Yes.
Yeah. Some of in the chat box, there are people are asking some questions, and I think I have also a little. I will be happy if you just clear us. So the question I asked you from the very first, because it's a very unfortunate. Although I am expressing my personal, I have lost my both the parents within 22 hours just a few days ago in this corona pandemic. Okay. But this is unfortunate, but the lives still go on, so we are here. So my point is actually what you are saying in the last 10 years when the Ebola comes and others in Africa, that was not so hugely affecting the whole 360 degree of the universe. From Wuhan to Italy, Italy to Greece, Greece to USA, USA to India and Africa, wherever. And the question someone is asking why there are so many variation in Spain, because this is an RNA virus. So actually the answer lies there. So you will basically uh, elaborate, I think, in the second part of this session. Obviously, I know. So that is the thing is this. But I am in little doubt. If you just little clarify or elaborately give this thing, if this is causing a droplet, if the what is saying by government, ICMR and all other things, or who just keeping a distance, what you are also saying, yeah, putting a mask and keeping a distance, because the droplets, they are heavy, they will go down, they will automatically within 6 meters they cannot cross after 6. But still, actually still, because I'm sorry, I'm a little bit what should I say, emotional, because when I took my parents to the hospital, believe me, every minute there are ambulances are coming. This is still I'm in a traumatic situation. Also, I handled 3-4 days with my parents in my hand with the medicines, steroids, and the oxygens. And when I found they are going down and down, I have with my friends who are doctors, as per their suggestion, I took them to hospital. The thing is, I found, and it's a still I am in a trauma that within 2 minutes, every minute the ambulances are coming, and these are there are 2 persons, 3 persons in each ambulance. So this I have never seen in my life. I have visited in so many occasions for the. So that is one thing. Still, I am in little bit doubt. Maybe emotional or I do not know. Ebola, SARS-1, CoV-1, which are as per your words, what I understood is more dangerous. But that doesn't create. But that didn't create such 360 of the universe, such a two-phase, second phase, and people are now saying the third phase is coming. So that is one thing I have in still in little doubt in my mind that I will be very obliged if you just say this little bit.
So let me. So first of all, my most heartfelt sympathies to people who've lost loved ones, not simply Professor Banerjee, but anybody at all. This is an awful time to be living through, and to live through it, struggling to keep your sense of proportion, your balance, struggling not to give in to fear. All of this is hard. So just no question about these being very difficult times. The distinctions I'm trying to make, in a sense, they're academic distinctions, and they don't really help one's own personal trauma particularly very much, but it's what we're dealing with. The distinction I'm trying to make is that when people are infected and the virus grows in the body in the first, let's say, 6 hours, what we are left with is a set of different possibilities and trajectories. And the real question is, the real limited question that I was trying to deal with is, to what extent are all these trajectories personally dangerous to the infected person? Remember that all these trajectories will involve a certain amount of throwing out of the virus, and therefore will add to virus transmission and will therefore add to the pandemic. But that's a separate issue from what happens within the body. And as I pointed out, depending on circumstances that for SARS-CoV-2 and COVID-19 we really don't understand particularly well, but depending on those, in a small minority of infected people, we have progression to serious disease. The best case estimates are that in more than half the people who are infected, there are either no symptoms or only transient symptoms, a certain amount of cough and cold and so on and so forth. I'm aware that this feels like cold comfort to people who've had family in severe illness in hospital and dying of disease. But at the population level, epidemiologically, you're still left with the reality that most people recover with no symptoms, mild symptoms, or moderate symptoms. The borderline between no symptoms and mild symptoms is quite subjective to a certain extent, because what is a mild symptom for somebody is no symptom for somebody else, and so on. In about 10 to 15% of cases of infection, people begin to have more and more severe symptoms. Now, is this because they have been infected with a much larger dose of the virus? Is it because they are elderly and or they are type 2 diabetic and or they have obesity related problems and or they have pre-existing lung disease, and as a consequence their inflammatory responses, um, on the one hand their baseline is high, and on the other hand their addition local enhancement of building microcontainment zones is slow, and therefore they have lung-wide infection to quite an extent before the full immune response kicks in. This is only speculation at the moment. There's some evidence supporting it, but it's all indirect evidence. We don't know this for a fact. This may be why the elderly, the diabetic, perhaps hypertensive, the chronic lung disease patients, the hyperobese patients, all tend to have a much higher frequency of severe illness. But it's certainly true that, again, amongst people who have severe illness, even there, by the time they have severe illness, they are getting good control of the virus. Virus counts begin to come down. There are exceptions where they begin to go up and down and fluctuate. But by and large, it seems to be this excessive situation of infection in too many places and inflammatory consequences in too many other places in the body that lead to two different outcomes that are so damaging that they cause death, which is number one, lung shutdown, and therefore requiring where even ventilators don't work, and then you require the extracorporeal membrane oxygenation, and that in the first place is not available in the bulk of India, even in metropolitan cities. And number two, that has its own problems because it is liable to bacterial growth and infection and so on and so forth. And secondly, the organ shutdown because of these, what I'm calling off-target effects of inflammatory responses. And it's really those that end up killing people. The proportions are still smaller. What is causing crowded hospitals is two things. Number one, what is causing crowded hospitals is the fact that SARS-CoV-2 is so easily transmissible that it does keep spreading in communities. And because it spreads in communities so rapidly, when you have huge numbers of infections per unit time, what you are having is even a very small minority of those numbers that are going to land up in hospitals are still enormous numbers. But the flip side of that, and I'm going to make a frankly policy point about this, the flip side of that is how many patients can your healthcare system deal with at a time? So let me point out some numbers. At its absolute peak last month and the month before, India's caseloads, right, in terms of new cases every day per million population, India's caseloads were about 300 to 320, 330 cases every day per million. Remember a time when Canada said we will not have flights coming in from India because India has massive caseload? And India's massive caseload at that time was this 300 and something per million. Canada's caseload a week before it banned flights from Canada was higher than India's. But Canada was not in as dire straits as India was, not because there weren't as many cases, but because the Canadian healthcare system was capable of taking in that many cases, absorbing that many cases, providing them the necessary health care, providing them every last damned detail of the necessary health care that every individual needed. And in India, we had the problem which all of us have read about in newspapers. Some of us, unfortunately, have experienced of ambulances taking seriously ill people from hospital to hospital, looking for admissions, looking for healthcare, looking for some way of getting the necessary healthcare. So the limitation varies from place to place. Let me point out, again underlining this number, 300 plus new cases per day in India. The peak in January in the United Kingdom was over 1,000 new cases per million population per day. I ask all of us to imagine what would have happened in India if India's numbers were of that kind.
So I am sorry, I am just stopping you. So still, what the statistics you are giving, if we consider that, do you think that in India still there is no community infection?
No, what do you mean? Of course, we've had everybody's had community infection. This ICMR-based pedantic definition of what is community transmission, what is not.
Yeah,
ICMR
because
makes a distinction between local transmission versus community transmission. What they mean by community transmission is countrywide community
yeah,
transmission.
yeah,
There is
yeah.
never going to be countrywide community transmission. This is a locally transmitted virus, but we've had local transmission for a year. Of course, we've had transmission in our communities all over the country.
Yeah, that's the point is, sometimes people are saying, now if in India we are quite afraid what will happen if there is a community
No,
infection.
no, 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 no. That's all just nonsense. But that's playing with words and sort of
Definitely.
bureaucracy trying to play with words. Let's get something clear. When infection goes from one person to another, that's transmission. That's it. And when you have small outbreaks coming up here and there in our villages, towns, and cities, without it being very obvious that one traveler from somewhere has caused this, then you already have local community transmission. So that you have local community transmission, and we've had it since last year, has been unequivocal. Any amount of what Professor Banerjee refers to as words is really just bureaucrats trying to play with words. Let's
Jargons by the bureaucrats.
let's not even go there. It's human tendency even amongst bureaucrats to say, no, don't worry so much. We don't have countrywide transmission. Sure, you don't have countrywide transmission. That's no help to people who are trying to deal with local transmission in their own communities. And look, we've had local transmission in our own communities in multitudinous places. I mean, out of 700 plus districts of the country, how many districts have shown on outbreaks over the past 3 months by now? Of course, we've had community transmission. Just no question about
Each and every. There is not a single uh, there is not a single district of the India where you will find there is not a single case.
Well, again, you talk to bureaucrats, they'll point out there's a handful of districts. But
No,
the
no, no.
fact
I'm
is,
not. I'm talking all over the country.
over
I'm just want to mention. I mean,
evidence
from
is that
Kashmir,
we have,
Kashmir to Kanyakumari, Gujarat to
we have
Assam,
very widespread.
everywhere.
We have very
It is
widespread.
a quite spread thing.
Of course.
Actually, that was my point of dispute, or that was my point of 10 years, 15 years ago when the Ebola or SARS was coming. It was not so spreading off.
No, certainly not. But that's
Yeah.
where we started, remember. Those are infections where outbreaks did not transform into widespread transmission because physical distancing will always reduce efficiency of transmission in a sort of quantitative sense. But for many of, for certainly for SARS and MERS, I'm not talking about Ebola. Ebola is a different problem altogether. But for SARS and MERS, the building distancing allowed transmission to drop so low that the outbreak essentially petered out, and that therefore there wasn't any substantial community transmission. It's the difference in transmissibility that is a major distinction I'm arguing. So that even though today's virus is less individually lethal, because it is this shotgun spray rapidly spreading virus, it's causing far more widespread damage.
That is if you compare, that is a one shotgun versus a stain gun.
Yes. So another question has been, I should not be keeping people from lunch. Another question has been about after how many days vaccine have to be taken after COVID infection, and memory cells will keep remain in the body for how many weeks. Hold the question. We will talk about that hopefully in the context of vaccine technology platforms and so on and so forth in the evening, if you don't mind, because otherwise answering that will sort of be an isolated response.
Okay, sir. It is now 1:15. If no other questions are there, we are really thankful for your talk, deliberation, and actually the questions what is still are there, and you have promised to answer all of them, especially with the how the mechanism, what is the mechanism of this infection spreading and all other things. We are waiting for that at 5 onwards. So may I request all the participants, please join. And sir, you will get actually I think you got the two links, one for this morning, and the all in the same mail you have the second link. And sir, I have already sent you what is I told you to kindly see, and whether I have done the right thing for you or not.
Sure.
And,
Don't worry about it. That's fine.
okay, and by send me by tomorrow.
I,
Okay,
I,
with the signature. Thank you so much. With this, may I request all the participants to join again by 4:55, so that we can not miss a single minute to hear from Professor Rao.
thank you.
Okay, thank you so much.
Thank you. Bye bye.
Thank you so much, sir. With your kind permissions, we are ending this session. We'll again resume from 5 p.m. sharp. Okay, sir. Thank you so much.
Thank you. Thank you all the participants looking to join